In this section, we discuss the materials that make up solar cells, a technology that is rapidly changing global energy production and will make a huge impact on society. Solar photovoltaics have dramatically reduced in cost during the 2000s, from very much out of reach to quite cost competitive. Now wind and solar are less expensive than coal, so there really is no economic reason to build new coal power plants. It already costs less than 1/3 of the cost per mile for the electricity of an electric car compared for the gas in a gasoline car. With a continued decrease in costs, we anticipate a time in the future where solar electricity might be practically free. In a photovoltaic, sunlight is absorbed, creating electron-hole pairs. The electrons are collected by the top, negative electrode, while the holes are collected by the bottom, positive electrode. What we see from the outside is the anti-reflection coatings and finger electrodes to maximize and not block the incoming light. Inside is typically a single crystal silicon p-n junction diode that helps separate the electrons and holes. When a photon makes an electron-hole pair in the depletion layer of a p-n junction, the charges created immediately feel the electric field from the built-in potential. The field makes the holes drift towards the p-type region and the electrons drift towards the n-type region. Note that these are non-equilibrium electrons and holes, so they are not driven by the equilibrium Fermi level that includes diffusion forces, until they thermalize. The drift potential is the same as the electron potential energy, so we can imagine the non-equilibrium electrons as being excited into states that are bent like the conduction and valence bands shown here. The electrons then slide down the conduction band towards the n-type side, and the holes float up towards the p-type side. Note that this is the direction of a reverse bias current. Forward bias is to drive majority electrons and majority holes towards each other. Here, the electrons and holes are moving to the opposite direction. So, if we don't let the charge or voltage build up by short-circuiting the device, there will be a reverse bias current arising from the photoexcitation. That is, the short-circuit current is negative and related to the photoexcitation rate. Recall that in the dark, the electrons and holes are all in equilibrium, meaning there is no free energy difference if they were to move. This is represented as a constant Fermi level or electrochemical potential of electrons. An external voltmeter would feel no electromotive force from this diode. When the junction is illuminated, electrons and holes are created and flow towards opposite ends. If these excess electrons and holes are not removed, the buildup of charge will induce a potential difference, driving newly created charges back, even after they thermalize. The direction of this voltage in the diode is the same as that for forward bias. In this non-equilibrium state, a non-equilibrium or quasi-Fermi level can be used to describe the chemical potential of the thermalized electrons at the electrodes in this diode. During illumination, an external voltage would be sensed from a voltmeter indicating that an electromotive force has arisen, meaning the photodiode is acting like a battery supplying an electric current and voltage. The output voltage can be described by the difference in the quasi-Fermi levels. This diagram also gives a simple justification as to why the output voltage of a PV cell is limited by the band gap. If the output voltage times E is greater than the band gap, there will be no built-in voltage left. The photovoltaic IV characteristics can be understood as a combination of a diode and a current source. In the dark, the photovoltaic is simply a diode. With zero bias, there is no current, V equals 0 and I equals 0. Under forward bias, there is a current where the turn-on voltage is related to the band gap. The equation for the current I is simply the diode equation. The current through the load is the same as the current in the diode. When the photovoltaic is illuminated, the number of electron-hole pairs formed is proportional to the light intensity and the quantum efficiency. The electron and hole pairs separate and create a current in the reverse bias direction, here shown as a negative current like a diode in reverse bias. Thus the short circuit current is negative and proportional to the light intensity. If the circuit is open, the load resistance is infinity or removed, the voltage builds up in the forward bias direction until the forward bias current cancels the photoinduced current at the open circuit voltage. In this example here, the I equals 0 open circuit voltage happens at about half the silicon bandgap voltage. The equivalent circuit of this description is an ideal current source given by the photoinduced current in the reverse direction along with a diode. The equation for the external current I with an external voltage V is given by the diode equation minus the photoinduced current. The IV curve of an illuminated photovoltaic looks like the diode IV curve shifted down by the photoinduced current. Power is delivered to the load when the photovoltaic acts like a battery. That is, when V is greater than 0, the diode is under forward bias, drives a current through the load, or I is less than 0, as if driven by the photoinduced current. Thus, the power-producing quadrant here is the V greater than 0, I less than 0 quadrant. The power output of a solar cell is I times V, which is maximized by the largest rectangle that fits within the IV curve. The load resistance that would draw this current at this voltage is R equals V over I. Notice that the current is less than the short circuit current and the voltage is less than the open circuit voltage. The maximum power, I max times V max, divided by the product of the short circuit current times the open circuit voltage, is called the fill factor. The fill factor is a measure of how close the solar cell IV curve is to the rectangle, the ideal shape, defined by the open circuit voltage and the short circuit current. In a typical PV, the photocurrent doesn't just come from the electron-hole pairs produced in the depletion region, but also within a minority carrier diffusion length of the junction. The light intensity will generally decay exponentially where the absorption length is a characteristic of the semiconductor. The side facing the light is often an N-type region made so thin that most of the light goes through the space charge region quickly. Some of the light also gets past the space charge region. Thus, electron-hole pairs are made before and after the space charge region, not just within. When photogeneration occurs within a diffusion length of the space charge region, they can also contribute to the photocurrent of the PV device. When minority carriers are photogenerated in neutral regions, they can diffuse to the space charge or depletion region and then drift towards the electrode where they can contribute to the photovoltaic current. If they recombine radiatively, producing light with energy of the semiconductor bandgap, then that light can be easily reabsorbed to produce new electron-hole pairs somewhere else. Thus, only non-radiative recombination is a loss. Photogenerated majority carriers are repelled from the space charge region and contribute to the photovoltaic power by thermalizing in the neutral region of the electrode. Thus, it is the photogenerated minority charge carriers that are critical to engineer in a photovoltaic. The thickness of the neutral regions should be larger than the minority carrier diffusion length, or there might be significant depositing of undesirable charge at the electrode or non-radiative recombination at the surface. Thus, the active region of the photovoltaic is not just the depletion region, but also anything within a recombination length of the junction. Because recombination length is related to diffusion coefficient and recombination time, which is also the mobility and recombination time, the mu-tau product is often considered an important materials metric for minority carrier devices such as photovoltaics. Also keep in mind that the absorption length depends on wavelength, with longer wavelength light penetrating into the device deeper, so different regions of the device might be more or less important for different wavelengths of incoming light. Recall that photon absorption depends on whether a semiconductor has a direct or indirect bandgap. Silicon with an indirect bandgap has low light absorption, so the devices need to be thick to absorb all the light efficiently. Typical silicon photovoltaic cells are around 200 microns thick, which makes them brittle and fragile. Direct bandgap semiconductors have a much higher light absorption enabling thin film photovoltaics. The semiconducting film is only a few microns thick, which makes them flexible and so less fragile when deposited on a flexible substrate. Sunlight contains light of all frequencies with intensity peaking in the visible. Even a perfect photovoltaic can only convert light with energy equal to the band gap with perfect efficiency. A perfect silicon solar cell can convert 1.1 eV light with 100% efficiency, where commercial solar cells do quite well, here about 75% efficiency for the 1.1 eV light. However, all the light with larger wavelength or lower energy don't even get absorbed, so their energy is not converted. Also, light with higher energy still only produces one electron-hole pair, where the energy above the band gap is lost during thermalization. So, the theoretical efficiency of even a perfect single-junction solar cell decreases at lower wavelengths, higher energy photons. The maximum theoretical efficiency of a single-junction photovoltaic is known as the Shockley quasar limit. At small band gaps, all the photons are converted, but the voltage they produce, limited by the band gap, is small, so the power output is low. At high band gaps, only the high energy photons are converted, while most of the photons with lower energy are wasted. Thus, the efficiency of a photovoltaic tends to peak around 1 to 1.5 electron volts, where silicon and gallium arsenide have their band gaps. Commercial silicon and gallium arsenide photocells now have efficiencies above 25%, close to the theoretical maximum. To convert sunlight more efficiently, a multi-junction cell can be used. For example, this triple junction cell has a high band gap indium gallium phosphide as the top cell, which converts the high energy ultraviolet and blue light while transmitting lower energy light to the cells below. The medium and small band gap indium gallium arsenide and germanium cells convert the lower energy green, red, and infrared light, leading to experimentally verified efficiencies up to 40%. Schottky junctions can also be used as a solar cell. The junction produces a small depletion layer and thus a built-in voltage, which can be used to separate photogenerated electron-hole pairs. Here, the electrons slide down, making the semiconductor the negative electrode, while the holes float up to make the metal a positive electrode. Many of the emerging PV materials, such as perovskite solar cells, organic solar cells, and dye-sensitized solar cells, have no explicit p-n junction. The active light absorber is an intrinsic semiconductor like an insulator. Instead, these photovoltaics rely on charge carrier selective contacts, where one electrode is an electron transporting layer and the other electrode is a hole transporting layer. Ideally, the Fermi level of the metals and band alignment with the insulator are such that photo-generated electrons drift to the electron contact, while photo-generated holes drift to the hole contact. The contacts should also not accept and therefore reflect the undesired charge carrier. In this way, a high quasi-Fermi level builds up on the electron side and a low quasi-Fermi level is established on the hole side, providing the external electromotive force. In summary, a photovoltaic generally has a heterostructure that can separate photoexcited electrons and holes. The photoactive region is a semiconductor or insulator that absorbs photons and makes electron-hole pairs with long enough lifetime to make it to the desired electrode before non-radiative recombination happens. The electron-hole separation can happen by drift because of the heterostructure producing a built-in electric field, or by selective electrodes which allow only one kind of charge carrier to diffuse in while reflecting the other type. The built-in voltage can be created by an NP junction like a silicon solar cell or a metal insulator junction. The usable thickness of the active region will be determined by the minority carrier lifetime and mobility. Efficient solar cells also make use of strategies to maximize the capture of light. such as the use of surface texturing to prevent reflection of the incoming sunlight.